So we had talked a bit about the fact that carbon has three-dimensionality and it has these 109-degree angles, and that this geometry is called tetrahedral. And we have a way of illustrating this geometry on a two-dimensional plate using some two-dimensional helper icons. What do I mean by that? And what I'm talking about is the dash and the wedges. And so you'll see dashes. Actually, I guess I'll just draw them out. So if I draw this as a static image, this methane here, you'll see that there is a hydrogen, and there often is a wedge thing that pops out towards you. So this is supposed to be the hydrogen that's coming out towards you. And then there's a hydrogen sort of over here. And that hydrogen, these two are of course the same, and that one's rotating around like so. And that's sort of the best way that we can depict this geometry. And this geometry, we've said, has bond angles of 109.5 degrees, and this geometry is called tetrahedral. All right, so that's a tetrahedral geometry. And essentially it comes down to the fact that if you really want to think about what this is made out of, you've got a couple of hydrogens that are just sphere-shaped, and a sphere shape back here, and this big sphere because it's coming out towards you, and this sphere right here. And in order for all these spheres to fit together comfortably, they need to be separated by about 109 degrees. Now, this molecule is rotating on its own, and of course molecules can diffuse and they undergo Brownian motion. But molecules, of course, rotate all the time. In fact, on this structure here, this hydrogen itself is rotating, and these hydrogens down here are rotating because this bond, it can rotate. So it's not fixed in place. It can behave sort of like an axle on a wheel. And that is a property of a sigma bond. So something to keep in mind, sigma bonds allow rotation. And so that means that the connections, atoms connected by sigma bonds, so if we just draw the sp3 bond of ethane that comes through here, all right, so ethane, and it has hydrogens that come out towards you, and a hydrogen goes away, and a hydrogen here, and say that hydrogen is coming out towards you, and that was going away from you. And it has, of course, a single bond through here, but this whole thing can rotate. So it can rotate, and that bond rotation can lead to a different conformation, a different conformational geometry, where now this hydrogen is down here, and now the hydrogen is here, and there's a hydrogen up here, right? And this hasn't changed, actually. That's still down there, that's still up here. But you can see, of course, that there's a rotation around here, and that gives you a slightly different looking molecule. It's constitutively the same, as in it has all the same bonds connected to the same atoms, but it is now different geometrically. All right, and so substituents can rotate around these individual single bonds, which allows these substituents that were down here or were up here. This one, as you can see in this image, actually turned around here. Of course, these are all symmetric molecules, so it can be kind of hard to really know what you're looking at, but this rotation has some interesting consequences because it's really not energy free, right? So in order for this bond to rotate, well, I kind of drawn that a little backwards. Let's try to keep consistent with my arrows. In order for, and I'll keep this green, this bond that's pointing out towards you to rotate that way to being in the plane of the paper, it kind of has to go past this hydrogen, right? Right, and so this is this rotation except animated. And one of the problems, of course, with drawing some of these things, these ball and stick models here, is that the hydrogens are actually sort of underrepresented. They're kind of big, or they're bigger than this. But that's okay, I can just sort of draw that up here. And then you can imagine that these hydrogens are likewise quite large up here. And when this thing rotates around and the hydrogens are directly across from each other, they come very close to bumping into each other. And that gives you a a higher energy configuration that is called an eclipsed configuration. And when they are straddling, that is called, when this straddles two different hydrogens over here, that is called a staggered conformation. And how we illustrate that, all right, and this is an important point, all right, is how we illustrate that is I'll draw this carbon here and the carbon going up here. So we'll know I am right now drawing that carbon right there. Then there's a hydrogen coming out towards you. All right, so that is that hydrogen right there. Then there's a hydrogen hiding behind everything, and it is here, and that is, of course, sort of peeking out right there. That's that hydrogen. All right, and then the spinning side, you can imagine you have two geometries that you can pick out of. There's the one where they're very nearly bumping into each other, where they're the closest to each other, and that we sort of can illustrate like this. Okay. And these two, you notice, are the same thing, where you have a hydrogen, it can look right across and it can see another hydrogen. And that is the eclipsed conformation, okay? In fact, let me write that a little bit neater because I lumped everything together. Eclipsed conformation, because they're eclipsed. And then in contrast to that, what I drew up here, let me get rid of these little circles so it's more clear. All right, what I drew up here is the staggered conformation. And it's staggered because this hydrogen, which is in the plane of the paper, when it looks across, it looks between this hydrogen that's popping out towards you and this hydrogen that's going away. So in this these two conformational isomers, there are staggered and eclipsed. Okay, so those are two words to get yourself familiar with. Now, sigma bonds allow for free rotation, but in contrast, pi bonds don't. So let's get this all out of the way. Now, pi bonds, of course, we discussed sort of exist in the plane above sigma bonds. So in an Sp2 hybridized system, there's a certain geometry that we kind of discussed, and then that Sp2 hybridized, there's S, remember, Sp2, right? So there's an S and two p orbitals, and then those are hybridized together, so that means there's one p orbital that's not hybridized. So in Sp2 hybridization would have your carbon here, and then you'd have your Sp2 sort of be bunny ears, and then it forms the sigma bond, right, through here. And you have that here, and you have that here, and these are your Sp2. And then, of course, your p orbital is just a p orbital, and that goes here and here. So your Sp2 has a sigma bond that goes through the center. And you can just draw that. And that would have free rotation because it's a sigma bond. But you can imagine this is sort of like a bike lock, this pi bond up here. So you cannot rotate around this sigma bond. This bond right here can't break, right? Because if this rotates, then it breaks. These two have to be in alignment. These p bonds have to be in alignment at all times. So you can't rotate it. If you rotate it, as I've drawn, you end up with a carbon, and you've got your Sp2 bonds. We'll draw sort of one bond going out of the plane and one bond coming out at you. And then you get the sigma bond in the plane, one bond coming away, one bond coming out at you, H. And then if you try to rotate it, right, well, it'll break. So if I just try to like, and then it's like, no, you can't go that way, I need to bond with you. So, yeah, you can't, there's no rotation around a pi bond. So that is a pretty big difference then between Sp2 and Sp3 bonding mechanisms, okay? So let's Actually, let's dive in a little bit because there's a couple of things to kind of unpack here, right? I drew this hydrogen as sort of going away, this hydrogen coming out at you. So what is this? First of all, what is this molecule? This molecule is called ethylene. Okay? And ethylene is composed of two bonding frameworks, all right? You have the Sp2 bonding framework that I drew up there in white, and this framework is planar, okay? So there's a bond inside of the plane of the paper, and then there is a bond that's coming out at you. Oops, turned into a... And it's popping out towards you, and there's a bond going away, okay? This is 120 degrees away. This is 120 degrees away, and this is 120 degrees away. So if you were to look at it straight down, so if this were your eyeball, and you're going to stare straight down from the very tippy top, this would look like a hydrogen all in the plane of the paper, hydrogen, and then your sigma bond, okay? So an sp2 bond has a bigger bond angle than an sp3 bond, because now a lot of that spinach that came from having 4 bonds to carbon, it's gone, right? Because now you only have actually really 3 different atoms connected to carbon. Carbon is attached to itself twice, so that means you have more room to breathe. So we can get rid of this business and go back and revisit this sort of unique geometry, right? So you got the sp framework, sp2 framework, I should say, and the sp2 framework is just composed of sigma bonds. And then you also have, so that's the sp2 framework. And then you also have the pi framework, which we just kind of needlessly can draw over on this side. And the pi framework is actually very simple. It's just a pi bond and a pi bond over here. And realistically, I guess you want to say there are 2 electrons, right? Because there are 2 electrons in the pi system, and they can be anywhere. But maybe it's easy for you to imagine that one of the electrons is sort of zooming around up here, and one of the electrons is zooming down here. They can, of course, be anywhere at any time. It's a probability distribution. But at the end of the day, you have this locked-in electron configuration that's sort of above and below the plane of the atom. So if you draw the whole thing, you draw it as a planar system where the hydrogens come out at you. It's rigid. It doesn't deviate from this planarity because it can't rotate because it's got these pi bonds that extend up and below. And there's an electron density that flows actually above and below as well. Although I will often just illustrate it flowing from one pi orbital to the other. It's actually kind of irrelevant because there's obviously electron density flowing between both. And so that geometry that it creates has some interesting effects for making sp2 molecules. It gives these things shape. Okay, so if we take this molecule, we take ethane and we rotate it so that the hydrogen goes up and this hydrogen goes down, right? So what does that look like? So if we just say rotate it, so now this is in the plane of the paper, H, 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 and then the P bonds are like coming out at you, like, and we're going to erase these, but that's sort of the idea. Is that these pi orbitals are now coming out at you, like they're popping out at you. All right, so that's the geometry. It's just sort of hard to draw, right? Well, if this can't rotate, then you have this inflectious geometry where this hydrogen will never be able to get away from staring at that hydrogen, right? They're always going to be eclipsed, which is an interesting thing to think about if they're not hydrogens, right? So if they're not hydrogens, if they're, say, carbons, then that gives you some really different molecular geometries. So you can imagine if what we'll say the eclipsed version, the wrong version, we'll draw a molecule where we have let's call it CH3. right? And then we're going to have a double bond here and a hydrogen here. And that's a CH3 down here, right? So these two CH3s, that's sort of eclipsed because these two big things are directly across from each other, all right? And when the two big things, when the two big substituents are directly across from each other, with a double bond, we don't call it eclipse, we call it cis, all right? Cis. A cis configuration. And so a cis configuration, you can probably imply, means that it's on the same side, that they have some sort of similarities. That's what cis means, of course. And then the other conformation would be where the CH3 is not staring at its friend. That is on the other side, and the hydrogen is here and the hydrogen is here. All right, so this CH3 only sees the hydrogen, and those are further apart. This actually has a name called not staggered, because that wouldn't make sense, right? Like in some ways, these are always eclipsed. But this is called trans. All right, so trans means apart or away. So essentially trans as in like transatlantic, as in these are separated, like you have to cross an ocean to get over to that side. And what's interesting, of course, is because you don't have free rotation like you do in the other system, these are not resonance structures, these are not different conform. They can't flip around. Under normal conditions, these are locked in place. These are not exchanging. Okay? So a cis and a trans compound, these are, important. You can probably think for a while people were making these so-called trans fats and butter that are bad for you. Well, it turns out lipids that you make and I make and probably other humans make as well are in the cis conformation. This is how we make our lipids. The cis conformation actually is a higher energy conformation because it puts two big things right next to each other so that when you break that, you get extra energy out. It's fairly efficient for your body to make cis conformations. Trans conformation, however, is thermodynamically stable. Things like to be in the trans conformation. So when you make an artificial fat, you tend to make these trans conformations because two big substituents don't like to be together. The problem, of course, is that your body doesn't deal with trans fats. There's really no efficient molecular machinery to break down trans fats like cis fats. And so there was a hullabaloo and everybody had to pull them out of their ingredients, right? So at the end of the day, though, these two different conformations, they're very important, and that sort of cis-trans fat discussion gets to a much more engaging aspect of chemistry, and that is these are two different compounds. I mean, they have the same molecular formula. They both come out to be, what is that, CH3, CH3. You can write them both that way, or 1, 2, 3, 4. So there's C4, 3, 4, 5, 6, 7, 8. H8, right? They're both exactly this, but they differ in how they connect to each other. And this difference, it's an important difference, is a difference that requires a word, right? And that means that we have to come up with a term that describes when two atoms differ in space, but not in molecular formula. And that term is isomers. All right, so isomers, as a natural consequence of this three-dimensionality of atoms, because you can put stuff together in different ways using the same pieces. And cis and trans are an example of two different isomers, all right? And so specifically, actually, they're two different examples of stereoisomers. So in isomers, all right? So they're examples of stereoisomers. So this is a difference I don't know why I keep hitting the erase button. Stereoisomers. Well, let's write down the definition of stereoisomers. Having the same formula, but differing in the three-dimensional arrangement. Now, you can, of course, have different isomers that are not based on three-dimensionality. So, for instance, you can have something called a constitutional isomers. And a constitutional isomer would look something like this. So the difference between these two configurations, right, where that's a CH3 and that's a CH3, and this, it would be a constitutional isomers. So the bonds in the constitutional isomer actually exist in different positions, right? So this is an sp3 carbon at the end, and this is an sp2 carbon. That's fundamentally different. There's a constitutional difference between these two compounds. So at the end of the day, that is sort of what separates these two. You can change hybridization. If you change hybridization from sp3 to sp2, or you start moving atoms around, for instance, this only has one hydrogen here and this has two, that would be a constitutional isomer. Of course, both of these have the same molecular formula. They continue to both be represented by C4H8, but they're connected differently. That's a constitutional isomer. In a stereoisomer, these two molecules are connected differently, but every carbon has the same number of constituents. This carbon still has one hydrogen and one carbon attached to it, just like up here. That's a distinction between a constitutional isomer, where this carbon has one carbon and a hydrogen attached to it, and this one has, well, that's a bad example actually. That's one of the few parts of that molecule where they're actually very similar. Let's go back to this one. In this system, this carbon has two carbons attached to it and one hydrogen, whereas in this case it has two carbons attached to it and two hydrogens. So that carbon is obviously connected differently. It has a different number of connections, which makes it constitutionally different. So the last thing I wanted to cover in this lecture is experimental evidence for resonance, and or at least experimental evidence for resonance, specifically affecting geometry. Okay, so what an example, the example that I want to illustrate is the amide. So amides are a carbonyl, so that's a carbon with a double bond, right? And they've got a nitrogen right next to them. And this structure here is an amide. Of course, nitrogen likes to have 3 bonds and carbon likes to have 4, so we can build all this up. And this is dimethylamide, or dimethylformamide is the actual name. So usually you'd call this a molecule DMF. It's a solvent used in organic chemistry. And there's a resonance structure. There's a resonance form right here where you can take this lone pair, push it down here, and then of course you can't have 5 bonds to carbon, and this oxygen already has a lone pair, but it doesn't mind claiming those two, and you end up with something that looks like this. Alright, so now oxygen has 3 lone pairs in 1 bond, which means it's got more electron density than it really would prefer, and it becomes negatively charged. And then, still hydrogen here, and then this nitrogen now has 4 bonds and no lone pairs, which means it has less electron density than it would prefer, and as a consequence it's positively charged. So this resonance here, of course, is not really equal, right? So the proportion of electron density that this side of this resonance structure would indicate that there's probably more electron density on these lone pairs, because there's lone pairs here, there's lone pairs here, or maybe you could think like there's just an equal distribution of electron density across this, right? So, you see there's electron flow, and then electron flow goes back and forth, and you think, well, there's probably, equal probability of an electron being here versus here, but that's not true, okay? There is actually a greater probability that the electron is going to be closer to the oxygen because the oxygen is more electronegative. So if you were really going to map the electron density of this, you could probably map it to look something like this, where you have sort of this larger proportion of electron density closer to here, but you definitely have this distribution throughout these three atoms, okay? So as a consequence of this electron distribution, dimethylformamide has a double bond character right here. Okay, so essentially, well, right there, I mean, just make it super clear that this carbon double bond nitrogen plus, for some reason that looks a little less like a, draw that again, carbon double bond here. There. This is like a double bond, right? So when we draw DMF, we don't draw it like that. We draw DMF like this, okay? But that's not telling 100% of the truth, right? This bond behaves like a double bond, which means if that's a double bond and double bonds don't rotate, or at least it acts a lot like a double bond and double bonds don't rotate, you would expect that these bonds, these methyl groups here, I can write them as methyl. I can also write them as CH3. Maybe that's what I'll write now because this is still very much in the beginning of the semester, so we're not going to shift them and call them methyls quite yet. We'll still call them CH3, right? And so if this has double bond character, that means that it's going to have a really hard time rotating. And yes, it does. As a matter of fact, it's not 100% a double bond, right? And that's not so this isn't 100% a double bond right here, and so that's not really a 100% of a double bond. And so that's really kind of where we get into the trick with resonance. So a bond that is essentially going to be a double bond forever and ever is not going to want to rotate. It doesn't. But if it has a resonance structure that greatly diminishes or greatly enhances double bond character, and this is kind of an idea you gotta get used to, is bonding having this sort of a flavor, if you will, and it's like wave-particle duality. It's hard to wrap your mind around it, but if you think of it under certain conditions, what properties do they adopt? And if I say that this has double bond character, then it must adopt some of the properties of a double bond without necessarily adopting all of them all the time. And as a consequence, the rotational barrier around here is pretty high. So you remember when I told you there was a rotational barrier of even ethane, right? So ethane has a rotational barrier because you've got these hydrogens that, when it rotates, they bump into each other. Well, that rotational barrier is even higher. Like, this is very small. This happens very quickly at room temperature. This happens very slowly at room temperature. So as a consequence, you can see by NMR spectroscopy, you can see by a number of spectroscopic techniques that these two methyl groups are actually not equivalent. And right now, what does that mean for you? Right now, that means what you need to do is wrap your head around the idea that rotation, it can be inhibited, or rotation is inhibited by pi bonding. And if it's clearly a pi bond, that is always a pi bond, it doesn't have a resonance contributor that makes it a single bond, then there's just going to be no rotation around that. Now, if you have a resonance structure that's a single bond, all right, well, if you have something that's drawn out as a single bond, but you can show resonance to it to make it a double bond, you have to ask yourself, all right, so how strong is this resonance structure, and how much does that slow, and how much does that mean that it's going to have pi character? And so since this resonance structure here, where oxygen gets electrons because it's more electronegative than nitrogen, that means that this is going to be a significant resonance contributor, and that double bond is going to be a significant resonance. It's going to impart a lot of double bond flavor, if you will, which means that this rotation is going to be affected.